Algorithms to live by the computer science of human decisions. Author, Brian Christian and Tom Griffiths. 10. Networking, how we connect. The term connection has a wide variety of meanings. It can refer to a physical or logical path between two entities. It can refer to the flow over the path. It can inferentially refer to an action associated with the setting up of a path. Or it can refer to an association between two or more entities, with or without regard to any path between them. Vint Cerf and Bob Can. Only connect. E.M. Forster. The long-distance telegraph began with a Portland Samuel F.B. Morse, standing in the chambers of the US Supreme Court on May 24, 1844, wiring his assistant Alfred Vail in Baltimore a verse from the Old Testament, "What hath God wrought?" The first thing we ask of any new connection is how it began, and from that origin, can't help trying to augur its future. The first telephone call in history, made by Alexander Graham Bell to his assistant on March 10, 1876, began with a bit of a paradox. "Mr. Watson, come here. I want to see you," a simultaneous testament to its ability and inability to overcome physical distance. The cell phone began with a Bose Motorola's Martin Cooper walking down 6th Avenue on April 3, 1973, as Manhattan pedestrians gawked, calling his rival Joel Angel at AT&T. "Joel, I'm calling you from a cellular phone." A real cellular phone, a handheld, portable real cellular phone. I don't remember exactly what he said, Cooper recalls, but it was really quiet for a while. My assumption was that he was grinding his teeth. And the text message began on December 3, 1992, with cheer. Neil Papworth at SEMA Group Telecoms wishing Vodafone's Richard Jarvis an early Merry Christmas. The beginnings of the internet were, somehow fittingly, much humbler and more inauspicious than all of that. It was October 29, 1969, and Charlie Klein at UCLA sent to Bill Duval at the Stanford Research Institute the first message ever transmitted from one computer to another via the ARPANET. The message was lodged or would have been, had the receiving machine not crashed after low. Verily, Klein managed to sound portentous and Old Testament despite himself. The foundation of human connection is protocol, a shared convention of procedures and expectations. From handshakes and hellos to etiquette, politesse, and the full gamut of social norms. Machine connection is no different. Protocol is how we get on the same page. In fact, the word is rooted in the Greek protokollon, first glue, which referred to the outer page attached to a book or manuscript. In interpersonal affairs, these protocols prove a subtle but perennial source of anxiety. I sent so and so a message however many days ago. At what point do I begin to suspect they never received it? It's now 12:05 PM and our call was set for noon. Are we both expecting each other to be the one calling? Your answer seems odd. Did I mishear you? Or did you mishear me? Come again. Most of our communication technology from the telegraph to the text has merely provided us with new conduits to experience these familiar person-to-person challenges. But with the internet, computers became not only the conduit, but also the endpoints, the ones doing the talking. As such, they've needed to be responsible for solving their own communication issues. These machine-to-machine problems and their solutions at once mimic and illuminate our own. Packet switching. What we now think of as the internet is actually a collection of many protocols, but the chief among them, so much so that it's often referred to more or less synonymously with the internet, is what's known as Transmission Control Protocol, or TCP. It was born from a 1973 talk and a 1974 paper by Vint Cerf and Robert Bob Can, who laid out a proposal for the language of as they imagined calling it an internetwork. TCP initially used telephone lines, but it's more appropriately regarded as the evolution of the mail rather than the phone. Phone calls use what's called circuit switching. The system opens a channel between the sender and the receiver, which supplies constant bandwidth between the parties in both directions, as long as the call lasts. Circuit switching makes plenty of sense for human interaction, but as early as the 1960s it was clear that this paradigm wasn't going to work for machine communications. As UCLA's Leonard Kleinrock recalls, I knew that computers, when they talk, they don't talk the way I'm now continuously. They go blast, and they're quiet for a while. A little while later, they suddenly come up and blast again. and you can't afford to dedicate a communications connection to something which is almost never talking, but when it wants to talk it wants immediate access. So we had to not use the telephone network, which was designed for continuous talking, the circuit switching network, but something else. The telephone companies, for their part, did not seem especially amenable to talk of a fundamental shift in their protocols. Moving away from circuit switching was considered lunatic utter heresy, in the words of networking researcher Van Jacobson. Clean Rock reminisces about his own encounters with the telecommunications industry. I went to AT&T, the biggest network of the time, and I explained to them, "You guys ought to give us good data communications." And their answer was, "What are you talking about? The United States is a copper mine. It's full of telephone wires. Use that." I said, no, you don't understand. It takes 35 seconds to set up a call. You charge me a minimum of 3 minutes, and I want to send 100 milliseconds of data. And their answer was, "Little boy, go away." So little boy went away and, with others, developed this technology which ate their lunch. The technology that ate circuit switching's lunch would become known as packet switching. In a packet switched network, rather than using a dedicated channel for each connection, senders and receivers atomize their messages into tiny shards known as packets and merge them into the communal flow of data, a bit like postcards moving at the speed of light. In such a network, what you might call a connection is a consensual illusion between the two endpoints, explains Apple networking expert Stuart Cheshire. There are no connections in the internet. Talking about a connection in the internet is like talking about a connection in the US mail system. You write letters to people and each letter goes independently, and you may have a correspondence that goes back and forth and has some continuity to it, but the US mail doesn't need to know about that. They just deliver the letters. Efficient use of bandwidth wasn't the only consideration driving research into packet switching in the 1960s. The other was nuclear war. Paul Barron at the Rand Corporation was trying to solve the problem of network robustness so that military communications could survive a nuclear attack that took out a sizable fraction of the network. Inspired by algorithms developed in the 1950s for navigating mazes, Barron imagined a design in which every piece of information could independently make its own way to its destination, even as the network was changing dynamically or being torn to tatters. This was the second demerit against circuit switching and its dedicated, stable connections. That very stability meant that a dropped call stayed dropped. Circuit switching just wasn't flexible or adaptable enough to be robust. And here too, packet switching could offer just what the times were calling for. In circuit switched networks, a call fails if any one of its links gets disrupted, which means that reliability goes down exponentially as the network grows larger. In packet switching, on the other hand, the proliferation of paths in a growing network becomes a virtue. There are now that many more ways for data to flow, so the reliability of the network increases exponentially with its size. Still, as Van Jacobson tells it, even after packet switching was devised, the phone companies were unimpressed. All the telco people said, with very loud voices, "That's not a network. That's just a crummy way to use our network. You're taking our wires, you're sending on the paths that we create, and you're putting a lot of extra gunk on it so that you use it really inefficiently." But from a packet switching point of view, the phone wires are just a means to an end. The sender and receiver don't actually care how the packets get delivered. The ability to operate agnostically over any number of diverse media would be packet switching's great virtue. After early networks in the late 60s and early 70s, such as the ARPANET, proved the viability of the concept, networks of all types began sprouting across the country, doing packet switching not only over copper phone wires, but over satellites and over radio. In 2001, a group of computer scientists in the Norwegian city of Bergen briefly even implemented a packet switching network over avian carriers, that is, packets written down on paper and tied to pigeons' feet. Of course, packet switching would not be without its own problems. For starters, one of the first questions for any protocol, human or machine, is, quite simply, how do you know your messages are getting through? Acknowledgement. No transmission can be 100% reliable. Bin Cerf and Bob Can. What hath God wrought wasn't just the first long-distance telegraph message sent in the United States. It was also the second. Alfred Vail sent the quotation back to Morse in the Supreme Court chambers as a way of confirming receipt. Now, Vail's reply could make Morse, and the US legislators gathered around him, confident that Morse's message had been received, presuming, of course, that Vail hadn't known the choice of message in advance. But what would make Vail confident that his confirmation had been received? Computer scientists know this concept as the Byzantine generals problem. Imagine two generals, on opposite sides of a valley, that contains their common enemy, attempting to coordinate an attack. Only by perfect synchronization will they succeed, for either to attack alone is suicide. What's worse, any messages from one general to the other must be delivered by hand across the very terrain that contains the enemy, meaning there's a chance that any given message will never arrive. The first general, say, suggests a time for the attack, but won't dare go for it unless he knows for sure that his comrade is moving too. The second general receives the orders and sends back a confirmation but won't dare attack unless he knows that the first general received that confirmation, since otherwise the first general won't be going. The first general receives the confirmation but won't attack until he's certain that the second general knows he did. Following this chain of logic requires an infinite series of messages, and obviously that won't do. Communication is one of those delightful things that work only in practice. In theory it's impossible. In most scenarios the consequences of communication lapses are rarely so dire, and the need for certainty rarely so absolute. In TCP, a failure generally leads to retransmission rather than death, so it's considered enough for a session to begin with what's called a triple handshake. The visitor says hello, the server acknowledges the hello, and says hello back. The visitor acknowledges that, and if the server receives this third message, then no further confirmation is needed, and they are off to the races. Even after this initial connection is made, however, there's still a risk that some later packets may be damaged, or lost in transit, or arrive out of order. In the postal mail, package delivery can be confirmed via return receipts. Online, packet delivery is confirmed by what are called acknowledgement packets, or ACKs. These are critical to the functioning of the network. The way that ACKs work is both simple and clever. Behind the scenes of the triple handshake, each machine provides the other with a kind of serial number, and it's understood that every packet sent after that will increment those serial numbers by one each time, like checks in a checkbook. For instance, if your computer initiates contact with a web server, it might send that server, say, the number 100. The ACK sent by the server will, in turn, specify the serial number at which the server's own packets will begin. Call it 5000, and also will say ready for 101. Your machine's ACK will carry the number 101, and will convey in turn ready for 5001. Note that these two numbering schemes are totally independent, and the number that begins each sequence is typically chosen at random. This mechanism offers a ready way to pinpoint when packets have gone astray. If the server is expecting 101, but instead gets 102, it will send an ACK to packet 102 that still says ready for 101. If it next gets packet 103, it will say, again, ready for 101. 3 such redundant ACKs in a row would signal to your machine that 101 isn't just delayed but hopelessly gone. So it will resend that packet. At that point, the server, which has kept packets 102 and 103, will send an ACK saying ready for 104 to signal that the sequence has been restored. All those acknowledgements can actually add up to a considerable amount of traffic. We think of, say, a large file transfer as a one-way operation, but in fact the recipient is sending hundreds of control messages back to the sender. A report from the second half of 2014 showed that almost 10% of upstream internet traffic during peak hours was due to Netflix, which we tend to think of as sending data almost exclusively downstream to users. But all that video generates an awful lot of ACKs. In the human sphere, the anxiety that the message is indeed being received similarly pervades conversation. A speaker might subconsciously append "you know" to the end of every sentence, and a listener, for their part, can't help but make a steady stream of nods. Yes, ayes, roger that's, 10-4s, ahas. We do this even face to face, but on a phone. call. Sometimes it's the only way to know the call is even still in progress. No wonder that the most successful 21st century marketing campaign for a wireless carrier featured a network engineer's quality control catchphrase, repeated again and again. Can you hear me now? When something goes wrong in that back and forth, we are often left with a question mark. As software blogger Tyler Treat says, in a distributed system, we try to guarantee the delivery of a message by waiting for an acknowledgement that it was received, but all sorts of things can go wrong. Did the message get dropped? Did the ACK get dropped? Did the receiver crash? Are they just slow? Is the network slow? Am I slow? The issues faced by the Byzantine generals, as he reminds us, are not design complexities, they are impossibility results. Earlier networking research, Vint Cerf notes, had been founded on the assumption that you could build a reliable underlying net. On the other hand, the internet was based on the assumption that no network was necessarily reliable and you had to do end-to-end retransmissions to recover. Ironically, one of the few exceptions to this is in transmitting the human voice. Real-time voice communications, such as Skype, typically do not use TCP, which underlies most of the rest of the internet. As researchers discovered in the early days of networking, using reliable, robust protocols with all their ACKs and retransmission of lost packets to transmit the human voice is overkill. The humans provide the robustness themselves. As Cerf explains, in the case of voice, if you lose a packet, you just say that again. I missed something. For this reason, phone services that automatically reduce background noise to silence are doing their users a major disservice. Background static is a continual reassurance that the call is still connected and that any silence is a deliberate choice by the other party. Without it, one must constantly confront the possibility that the call has dropped and constantly offer reassurances that it has not. This too is the anxiety of all packet switching protocols, indeed of any medium rooted in a synchronous turn-taking, be it letter writing, texting, or the tentative back and forths of online dating. Every message could be the last, and there is often no telling the difference between someone taking their time to respond and someone who has long since ended the conversation. So how exactly should we handle a person or a computer that's unreliable? The first question is how long a period of non-responsiveness we should take to constitute a breakdown. Partly this depends on the nature of the network. We start to worry in a matter of seconds over the phone, days over email, and weeks over postal mail. The longer the round-trip time between sender and receiver, the longer it takes a silence to be significant, and the more information can be potentially in flight before the sender realizes there's a problem. In networking, having the parties properly tune their expectations for the timeliness of acknowledgements is crucial to the system functioning correctly. The second question, of course, once we do recognize a breakdown, is what exactly we should do about it. Exponential backoff, the algorithm of forgiveness. The world's most difficult word to translate has been identified as Ilunga, from the Chiluba language spoken in southeastern Dr. Congo. Ilunga means a person who is ready to forgive any abuse for the first time, to tolerate it a second time, but never a third time. BBC News. If at first you don't succeed, try again. T.H. Palmer. Today we expect our devices to communicate wirelessly even when wires would be easy. Our keyboard and mouse, for instance, talking wirelessly with a computer sitting inches away. But wireless networking began as a matter of necessity in a place where no wires could do the job, Hawaii. In the late 60s and early 70s, Norman Abramson at the University of Hawaii in Honolulu was trying to link together the university's 7 campuses and many research institutes spread across 4 islands and hundreds of miles. He hit upon the idea of implementing packet switching via radio rather than the phone system, connecting the islands with a loose chain of transmitters and receivers. This system would come to be known as the AlohaNet. The biggest hurdle that the AlohaNet had to overcome was interference. Sometimes 2 stations would transmit at the same moment, inadvertently jamming one another's signals. This is, of course, a familiar feature in human conversation as well. If both stations simply retransmitted right away to try to get their message across, they'd run the risk of getting stuck in perpetual interference forever. Clearly the Elohonid protocol was going to need to tell competing signals how to give each other space, how to yield and make way for one another. The first thing that the senders need to do here is what's called breaking symmetry. As any sidewalk pedestrian knows, dodging right as an oncoming walker dodges left, and then having both of you simultaneously dodge back the other way doesn't solve anything. It's the same story when two speakers both pause, make gestures of deference to the other, and then start to speak again at the same time, or when two cars at an intersection, each having stopped to yield to the other, try to accelerate and sync. This is an area where the use of randomness becomes essential indeed. Networking wouldn't be possible without it. One straightforward solution is to have each station flip a coin. Heads, it retransmits. Tails, it waits a turn, then retransmits. Surely one of them will get through uncontested before long. This works well enough when there are only 2 senders. But what if there are 3 simultaneous signals? Or 4? It would take a 1 in 4 chance for the network to get even a single packet through at that point, after which you'd still have 3 conflicting stations left, and perhaps even more competing signals arriving meanwhile. As the number of conflicts increases further, the network's throughput could simply fall off a cliff. A 1970 report on the Elohonid said that above mere 18.6% average utilization of the airwaves, the channel becomes unstable and the average number of retransmissions becomes unbounded. Not good. So, what to do? Is there a way to make a system that could avoid this fate? The breakthrough turned out to be increasing the average delay after every successive failure, specifically doubling the potential delay before trying to transmit again. So after an initial failure, a sender would randomly retransmit either 1 or 2 turns later. After a second failure, it would try again anywhere from 1 to 4 turns later. A third failure in a row would mean waiting somewhere between 1 and 8 turns, and so on. This elegant approach allows the network to accommodate potentially any number of competing signals. Since the maximum delay length, 2, 4, 8, 16, forms an exponential progression, it's become known as exponential backoff. Exponential backoff was a huge part of the successful functioning of the Elohonid beginning in 1971, and in the 1980s it was baked into TCP, becoming a critical part of the internet. All these decades later, it still is. As one influential paper puts it, for a transport endpoint embedded in a network of unknown topology, and with an unknown, unknowable and constantly changing population of competing conversations, only one scheme has any hope of working exponential backoff. But it is the algorithm's other uses that suggest something both more prescriptive and more profound. Beyond just collision avoidance, exponential backoff has become the default way of handling almost all cases of networking failure or unreliability. For instance, when your computer is trying to reach a website that appears to be down, it uses exponential backoff, trying again 1 second later, again a few seconds after that, and so forth. This is good for everyone. It prevents a host server that's down from getting slammed with requests as soon as it comes back online, and it prevents your own machine from wasting too much effort trying to get blood from a stone. But interestingly, it also does not force or allow your machine to ever completely give up. Exponential backoff is also a critical part of networking security when successive password failures in logging into an account are punished by an exponentially increasing lockout period. This prevents a hacker from using a dictionary attack against an account, cycling through potential password after password until eventually they get lucky. At the same time, it also solves another problem. The account's real owner, no matter how forgetful, is never permanently locked out after some arbitrary cutoff. In human society, we tend to adopt a policy of giving people some finite number of chances in a row, then giving up entirely. 3 strikes, you're out. This pattern prevails by default in almost any situation that requires forgiveness, lenience, or perseverance. Simply put, maybe we are doing it wrong. A friend of ours recently mused about her childhood companion who had a disconcerting habit of flaking on social plans. What to do? Deciding once and for all that she'd finally had enough and giving up entirely on the relationship seemed arbitrary and severe, but continuing to persist in perpetual rescheduling seemed naive, liable to lead to an endless amount of disappointment and wasted time. Solution: exponential backoff on the invitation rate. Try to reschedule in a week, then 2, then 4, then 8. The rate of retransmission goes towards 0, yet you never have to completely give up. Another friend of ours agonized about whether to offer shelter and financial assistance to a family member with a history of drug addiction. She couldn't bear to give up hope that he would turn things around, and couldn't bear the thought of turning her back on him for good. But she also couldn't bring herself to do all that it required to have him in her house, buying him clothes and cooking for him, reopening bank accounts for him, and driving him to work each morning when at some mysterious and abrupt moment he would take all the money and disappear, only to call again several weeks later and ask to be forgiven and taken back in. It seemed like a paradox, a cruel and impossible choice. Exponential backup isn't a magic panacea in cases like this, but it does offer a possible way forward. Requiring an exponentially increasing period of sobriety, for instance, would offer a disincentive to violate the house rules again. It would make the family member prove ever more assiduously that he was serious about returning, and would protect the host from the otherwise continuous stress of the cycle. Perhaps most importantly, the host would never have to tell her relative that she'd given up on him for good, or that he was beyond redemption. It offers a way to have finite patience and infinite mercy. Maybe we don't have to choose. In fact, the past decade has seen the beginnings of a quiet revolution in the way the justice system itself handles community supervision for drug offenders. That revolution is being spearheaded by a pilot program called HOPE, which uses the exponential backup principles of the Elohimate and which, in a striking coincidence, began at the birthplace of the Elohimate itself, Honolulu. Shortly after being sworn into Hawaii's First Circuit Court, Judge Stephen Allen noticed a remarkable pattern. Probationers would repeatedly violate their probation terms, and circuit judges would routinely use their discretion to let them off with a warning. But at some point, perhaps after a dozen or more violations, the judge would decide to be strict and assign the violator a prison sentence measured in years. Says Alm, I thought, what a crazy way to try to change anybody's behavior. So Alm proposed almost exactly the opposite, in place of violation hearings scheduled a long time into the future, requiring uncertain judgment calls, and occasionally producing huge penalties. HOPE is based on immediate predefined punishments that begin with just 1 day in jail and increase after each incident. A 5-year study by the Department of Justice reported that HOPE probationers were half as likely as regular probationers to be arrested for a new crime or have their probation revoked. And they were 72% less likely to use drugs. 17 states have followed Hawaii's lead and launched their own versions of HOPE. Flow control and congestion avoidance. The first efforts at computer networking focused on establishing reliable transmissions over unreliable links. These efforts proved to be so successful that a second concern immediately arose, making sure that an overloaded network could avoid catastrophic meltdown. No sooner had TCP solved the problem of getting data from point A to point B than it was confronted with the problem of gridlock. The most significant early warning came in 1986 on a line connecting the Lawrence Berkeley Laboratory and the UC Berkeley campus, which are separated by about the length of a football field. At Berkeley, the space happens to be filled with an actual football field. One day, the bandwidth of that line dropped abruptly from its typical 32,000 bits per second to just 40 bits per second. The victims, Van Jacobson at LBL and Michael Carrolls at UCB, were fascinated by this sudden factor of 1,000 drop in bandwidth and embarked on an investigation of why things had gotten so bad. Meanwhile, they heard murmurings from other networking groups across the country who were running into the same thing. Jacobson began looking into the underlying code. Is there some mistake in the protocol? He wondered. This thing was working on smaller scale tests, and then it suddenly fell apart. One of the biggest differences between circuit switching and packet switching emerges in how they deal with congestion. In circuit switching, the system either approves a channel request or denies it outright if the request cannot be accommodated. That's why, if you've ever tried using a phone system during some peak time, you may have encountered the special information tone and message proclaiming that all circuits are busy. Packet switching is radically different. The phone system gets full, the mail system gets slow. There's nothing in the network to explicitly tell a sender how many other senders there are, or how congested the network is at any given moment, and the amount of congestion is constantly changing. Therefore, the sender and receiver must not only communicate but meta-communicate. They need to figure out how fast the data should be sent. Somehow, a sorted packet flows without explicit management or coordination must both get out of each other's way and quickly take advantage of any newly available space. The result of Jacobson and Carroll's detective work was a revised set of flow control and congestion avoidance algorithms, one of the biggest modifications to TCP in 40 years. At the heart of TCP congestion control is an algorithm called additive increase, multiplicative decrease, or AIMD. Before AIMD kicks in, a new connection will ramp up its transmission rate aggressively. If the first packet is received successfully, it sends out 2 more. If both of those get through, it sends out a batch of 4, and so on. But as soon as any packet stack does not come back to the sender, the AIMD algorithm takes over. Under AIMD, any fully received batch of packets causes the number of packets in flight not to double but merely to increase by 1, and dropped packets cause the transmission rate to cut back by half, hence the name additive increase, multiplicative decrease. Essentially, AIMD takes the form of someone saying, a little more, a little more, a little more, whoa, too much, cut way back, okay, a little more. Thus it leads to a characteristic bandwidth shape known as the TCP sawtooth steady upward climbs punctuated by steep drops. Why such a sharp asymmetrical decrease? As Jacobson and Carroll's explain, the first time AIMD kicks in is when a connection has experienced the first dropped packet in its initial aggressive ramping up phase. Because that initial phase involved doubling the rate of transmission with every successful volley, cutting the speed back by half as soon as there's been a problem is entirely appropriate. And once a transmission is in progress, if it starts to falter again, that's likely to be because some new connection is competing for the network. The most conservative assessment of that situation, namely, assuming you were the only person using the network and now there's a second person taking half the resources, also leads to cutting back by half. Conservatism here is essential. A network can stabilize only if its users pull back at least as fast as the rate at which it is being overloaded. For the same reason, a merely additive increase helps stabilize things for everyone, preventing rapid overload and recovery cycles. Though such a strict distinction between addition and multiplication is the kind of thing unlikely to be found in nature, the TCP sawtooth does find resonance in various domains, where the idea is to take as much as one can safely get away with. In a serendipitous 2012 collaboration, for instance, Stanford ecologist Deborah Gordon and computer scientist Balaji Prabhakar discovered that ants appear to have developed flow control algorithms millions of years before humans did. Like a computer network, an ant colony faces an allocation problem in trying to manage its flow, in this case, the flow of ants heading out to forage for food under variable conditions that may sharply affect the rate at which the ants make successful round trips. And like computers on the internet, ants must solve this shared problem without the benefit of a central decision maker, instead developing what Gordon calls control without hierarchy. It turns out the ant's solution is similar to a feedback cycle, where successful foragers prompt more to leave the nest, while unsuccessful returnees result in a diminishment of foraging activity. Other animal behavior also evokes TCP flow control, with its characteristic sawtooth. Squirrels and pigeons going after human food scraps will creep forward a step at a time, occasionally leap back, then steadily creep forward again. And it may be that human communications themselves mirror the very protocols that transmit them. Every text message or email reply encourages yet another, while every unreturned message stanches the flow. More broadly, AIMD suggests an approach to the many places in life where we struggle to allocate limited resources in uncertain and fluctuating conditions. The satirical Peter principle, articulated in the 1960s by education professor Lawrence J. Peter, states that every employee tends to rise to his level of incompetence. The idea is that in a hierarchical organization, anyone doing a job proficiently will be rewarded with a promotion into a new job that may involve more complex and/or different challenges. When the employee finally reaches a role in which they don't perform well, their march up the ranks will stall, and they will remain in that role for the rest of their career. Thus it stands to reason, goes the ominous logic of the Peter principle, that eventually every spot in an organization will come to be filled by someone doing that job badly. Some 50 years before Peter's formulation, Spanish philosopher José Ortega y Gasset in 1910 voiced the same sentiment. Every public servant should be demoted to the immediately lower rank, he wrote, because they were advanced, until they became incompetent. Some organizations have attempted to remediate the Peter principle by simply firing employees who don't advance. The so-called Cravath system, devised by leading law firm Cravath, Swain and Moore, involves hiring almost exclusively recent graduates, placing them into the bottom ranks, and then routinely either promoting or firing them over the following years. In 1980, the US Armed Forces adopted a similar up or out policy with the Defense Officer Personnel Management Act. The United Kingdom has likewise pursued what they call Manning control, to great controversy. Is there any alternative, any middle path between the institutional stagnation of the Peter principle and the draconian severity of the up or out system? The AIMD algorithm can offer just such an approach, since it is explicitly designed to handle the demands of a volatile environment. A computer network must manage its own maximum transmission capacity, plus the transmission rates of its clients, all of which may be fluctuating unpredictably. Likewise, in a business setting, a company has a limited pool of funds to pay for its operations, and each worker or vendor has a limited capacity for the amount of work they can do, and the amount of responsibility they can handle. Everyone's needs, capacities, and partnerships are always in flux. The lesson of the TCP sawtooth is that in an unpredictable and changing environment, pushing things to the point of failure is indeed sometimes the best, or the only, way to use all the resources to their fullest. What matters is making sure that the response to failure is both sharp and resilient. Under AIMD, every connection that isn't dropping the ball is accelerated until it isn't, then it's cut in half, and immediately begins accelerating again. And though it would violate almost every norm of current corporate culture, one can imagine a corporation in which, annually, every employee is always either promoted a single step up the org chart or sent part of the way back down. As Lawrence J. Peter saw it, the insidious Peter principle arises in corporations because of the first commandment of hierarchical life: the hierarchy must be preserved. TCP, in contrast, teaches the virtues of flexibility. Companies speak of flat hierarchies and tall hierarchies, but they might consider speaking of dynamic ones. Under an AIMD system, no one is long anxious about being overtaxed, nor long resentful about a missed promotion. Both are temporary and frequent correctives, and the system hovers near its equilibrium despite everything changing all the time. Perhaps one day we'll speak, not of the arc of one's career, but rather of its sawtooth. Backchannels, flow control in linguistics. Looking into networking's flow control makes it clear that upstream MAC packets not only acknowledge and confirm transmissions, but shape the contours of the entire interaction, its pace and cadence. This offers us both a reminder and an insight into how important feedback is to communication. In TCP, as we've seen, there's no such thing as a one-way transmission. Without consistent feedback, the sender will slow down almost immediately. Curiously, the rising awareness of the critical role of feedback in the field of networking mirrored an almost identical set of developments going on around the same time in the linguistics community. In the middle of the 20th century, linguistics was dominated by the theories of Noam Chomsky, which considered language in its most perfect and ideal state, perfectly fluent grammatical uninterrupted sentences, as if all communication were written text. But starting in the 1960s and 70s, a surge of interest in the practical aspects of spoken language revealed just how elaborate and subtle the processes are that govern turn-taking, interruption, and composing a sentence or story on the fly, while being attuned to a listener's reactions every step of the way. What emerged was a vision of even ostensibly one-way communication as a collaborative act. As linguist Victor Ingves would write in 1970, in fact, both the person who has the turn and his partner are simultaneously engaged in both speaking and listening. This is because of the existence of what I call the back channel, over which the person who has the turn receives short messages such as "yes" and "aha" without relinquishing the turn. An examination of human back channels opened a whole new horizon for the field of linguistics, prompting a complete re-evaluation of the dynamics of communication, specifically the role of the listener. In one illustrative study, a team led by Janet Bavalis at the University of Victoria investigated what would happen when someone listening to a personal story got distracted, not what would happen to the listener's comprehension, but what would happen to the story. With poor feedback, they discovered the story falls apart. Narrators who told close-call stories to distracted listeners told them less well overall and particularly poorly at what should have been the dramatic conclusion. Their story endings were abrupt or choppy, or they circled around and retold the ending more than once, and they often justified their story by explaining the obvious close call. We've all had the experience of talking to someone whose eyes drifted away to their phone, perhaps making us wonder whether our lackluster storytelling was to blame. In fact, it's now clear that the cause and effect are often the reverse. A poor listener destroys the tale. Understanding the exact function and meaning of human back channels continues to be an active area of research. In 2014, for instance, Santa Cruz's Jackson Tillins and Jane Foxtree demonstrated that those inconspicuous ahs and yeahs, and HMMs and OHS that pepper our speech perform distinct, precise roles in regulating the flow of information from speaker to listener, both its rate and level of detail. Indeed, they are every bit as critical as ACs are in DCP. Says Tullins. Really, while some people may be worse than others, bad storytellers can at least partly blame their audience. This realization has had the unexpected side effect of taking off some of the pressure when he gives lectures, including, of course, lectures about that very result. Whenever I give these back-channel talks, I always tell the audience that the way they are back-channeling to my talk right now is changing what I say. He jokes. So they are responsible for how well I do. Buffer bloat. It's the latency. Stupid. Developing effective active cue management has been hampered by misconceptions about the cause and meaning of cues. Kathleen Nichols and Van Jacobson. It was the summer of 2010, and like many parents, Jim Jettis was fielding frequent complaints from his children that the family Wi-Fi network was running slowly. Unlike most parents, though, Jettis has worked at HP, Alcatel-Lucent, the World Wide Web Consortium, and the Internet Engineering Task Force. He was literally the editor, in 1999, of the HTTP specification still in use today. So where most geek dads would look into the problem, Jettis looked into the problem. As Jettis would explain to a room full of Google engineers, with networking jargon giving way to an urgent and unmistakable conviction. I happened to be copying, or syncing, the old X Consortium archives from my house to MIT over this 10 millisecond long path. Smoke ping was reporting latencies averaging well over 1 second, along with bad packet loss, just while copying a file. I took Wireshark, and there were these bursts of really strange behavior. This looked like no TCP, sawtooth, I expected at all. It should never occur that way. In plain English, he saw something very weird. As the saying goes, the most exciting phrase to hear in science, the one that heralds new discoveries, is not "Eureka," but "that's funny." At first Jettis thought that something was wrong with his cable modem. What his family had been calling a problem in the internet seemed like a traffic jam at their own wall socket. Packets meant for Boston weren't getting stuck midway there, they were getting stuck in the house. But the deeper Jettis looked into it, the more concerned he grew. The problem didn't affect just his home router and modem, but every home router and modem. And the problem wasn't just in networking devices, it was in computers themselves, in desktops, laptops, tablets, and smartphones, woven into Linux, Windows, and OS X. And it wasn't just in end-user hardware either, it touched the very infrastructure of the internet itself. Jettis sat down to lunches with key players at Comcast, Verizon, Cisco, and Google, including Van Jacobson and Vint Cerf, and slowly started to piece the puzzle together. The problem was everywhere, and the problem was buffer bloat. A buffer is essentially a queue whose function is to smooth out bursts. If you walked into a donut shop at roughly the same time as another customer, it wouldn't do for the very momentarily overwhelmed cashier to make one of you leave the store and come back another time. Customers wouldn't have it, of course, but neither would management. Such a policy is virtually guaranteed to underutilize the cashier. Putting the customers in a queue instead ensures that the average throughput of the store approaches its maximum throughput. That's a good thing. This superior resource utilization comes with a very real cost: However, delay. When Tom took his daughter to a Cinco de Mayo festival in Berkeley, she set her heart on a chocolate banana crepe, so they got in line and waited. Eventually after 20 minutes Tom got to the front of the line and placed his order. But after paying, they then had to wait 40 more minutes to actually get the crepe. Like Jim Jettis, Tom quickly found himself fielding a substantial volume of familial complaints. Taking orders turned out to take less time than making crepes, so the queue to order was just the first part of the problem. At least it was visible, though. Customers knew what they were in for. The second longer queue was invisible. So in this case it would have been a much happier outcome for all if the crepe stand had just cut off the line at some point and put up a sign that they weren't taking orders for a bit. Turning customers away would have made everyone better off whether they ended up in a shorter crepe line or went elsewhere. And wouldn't have cost the crepe stand a dime of lost sales, because either way they can only sell as many crepes as they can make in a day, regardless of how long their customers are waiting. This is precisely the phenomenon that Jim Jettis was observing in his home cable modem. Because he was uploading a file, his computer was sending the modem as many upstream packets as it could handle. And the modem was pretending to handle a lot more than it actually could, turning none away while building up a massive queue. So when Jettis tried to download something at the same time to visit a web page or check email, his ACK packets would get stuck behind the upload, having to wait in line at the modem to leave the house. Because his ACKs then took forever to return to the web and email servers, the servers would in turn throttle their own downstream connection speeds to a corresponding crawl. It was like trying to have a conversation where every time you say how it is delayed by 10 or 20 seconds, the speaker is going to slow way down, assuming you aren't comprehending them, and there's nothing you can do about it. When a networking buffer fills up, what typically happens is called tail drop, an unceremonious way of saying that every packet arriving after that point is simply rejected and effectively deleted. Turning new customers away from the crepe stand once the line gets too long would be a version of tail drop in a human context. Given the postal metaphor for packet switching, it might seem a bit odd to imagine a mail carrier who simply vaporizes every parcel that doesn't fit onto the truck that morning. Yet it's precisely such packet drops that lead a computer to notice that one of its packets hasn't been acknowledged, prompting AIMD to start halving the bandwidth. Dropped packets are the internet's primary feedback mechanism. A buffer that's to large a restaurant taking every order, no matter how short-staffed the kitchen. A modem taking every packet that comes in regardless of how long it'll take to send them on prevents this moderation from happening as it should. Fundamentally, buffers use delay known in networking as latency in order to maximize throughput. That is, they cause packets or customers to wait to take advantage of later periods when things are slow. But a buffer that's operating permanently full gives you the worst of both worlds, all the latency and none of the give. Smoothing out bursts is great if you are, on average, clearing things at least as quickly as they're arriving, but if your average workload exceeds your average work rate, no buffer can work miracles. And the bigger the buffer is, the further behind you'll get before you start signaling for help. One of the fundamental principles of buffers, be they for packets or patrons, is that they only work correctly when they are routinely zeroed out. For decades, computer memory was sufficiently expensive that there was simply no reason to build modems with oodles of unnecessary memory capacity. Thus, there had simply been no way for a modem to build up a queue bigger than it could handle. But at some point, as economies of scale in the computer industry radically lowered the cost of memory, modem manufacturers started giving their machines gigabytes of RAM, because that was effectively the smallest amount of RAM they could get. As a result, the ubiquitous device buffers in modems, routers, laptops, smartphones, and in the backbone of the internet itself became thousands of times too big before people like Jim Jettis sounded the alarm to do something about it. Better never than late. Take your most basic problem as a single person. Someone likes you, you don't like them back. At one point, that used to be kind of an awkward situation. You had to have a conversation. It was weird. Now what do? Someone likes you, you don't like them back? You just pretend to be busy forever. As isn't 3. Now is better than never, although never is often better than right now. The Zen of Python. Singer Katy Perry has 107% more Twitter followers than her home state of California has people. The most followed person on Twitter. As of early 2016, she counts some 81.2 million accounts among her fans. This means that even if 99% of her fans never message her at all, and even if that most devoted 1% who message her do so only once per year, then she still gets 2,225 messages a day, every single day. Imagine if Perry were committed to answering each fan message and the order received. If she could reply to 100 a day, then the fans' expected wait time for a response would soon be measured in decades. It's fair to imagine that most fans would prefer a slim chance of getting a reply right away to a guaranteed reply 10 or 20 years hence. Note that Perry doesn't have this problem when she leaves a venue and must run a gauntlet of fans expecting an autograph or a few words. Perry does what she can, moves on, and the lost opportunities dissipate. The body is its own flow control. We can't be in more than one place at one time. At a crowded party, we inevitably participate in less than 5% of the conversation and cannot read up or catch up on the remainder. Photons that miss the retina aren't cute for later viewing. In real life, packet loss is almost total. We use the idiom of drop balls almost exclusively in a derogatory sense, implying that the person in question was lazy, complacent, or forgetful. But the tactical dropping of balls is a critical part of getting things done under overload. The most prevalent critique of modern communications is that we are always connected. But the problem isn't that we are always connected, we are not. The problem is that we are always buffered. The difference is enormous. The feeling that one needs to look at everything on the internet, or read all possible books, or see all possible shows, is buffer bloat. You miss an episode of your favorite series and watch it an hour, a day, a decade later. You go on vacation and come home to a mountain of correspondence. It used to be that people knocked on your door, got no response, and went away. Now they are effectively waiting in line when you come home. Heck, email was deliberately designed to overcome tail drop. As its inventor, Ray Tomlinson, puts it, at the time there was no really good way to leave messages for people. The telephone worked up to a point, but someone had to be there to receive the call. And if it wasn't the person you wanted to get, it was an administrative assistant or an answering service or something of that sort. That was the mechanism you had to go through to leave a message. So everyone latched onto the idea that you could leave messages on the computer. In other words, we asked for a system that would never turn a sender away, and for better or worse we got one. Indeed, over the past 15 years, the move from circuit switching to packet switching has played itself out across society. We used to request dedicated circuits with others, now we send them packets and wait expectantly for ACKs. We used to reject, now we defer. The much lamented lack of idleness one reads about is, perversely, the primary feature of buffers, to bring average throughput up to peak throughput. Preventing idleness is what they do. You check email from the road, from vacation, on the toilet, in the middle of the night. You are never ever bored. This is the mixed blessing of buffers, operating as advertised. Vacation email autoresponders explicitly tell senders to expect latency. A better one might instead tell senders to expect tail drop. Rather than warning senders of above average queue times, it might warn them that it was simply rejecting all incoming messages. And this doesn't need to be limited to vacations. One can imagine an email program set to auto-reject all incoming messages once the inbox reached, say, 100 items. This is ill-advised for bills and the like, but not an unreasonable approach to, say, social invitations. The idea of encountering a full inbox or full voicemail is an anachronism now, a glaring throwback to the late 20th century and the early 2000s. But if the networks that connect our newfangled phones and computers with their effectively infinite storage are still deliberately dropping packets when things get fast and furious, then maybe there's reason to think of tail drop not as the lamentable consequence of limited memory space, but as a purposeful strategy in its own right. As for network buffer bloat, the ongoing story is a complicated but happy one, involving large-scale efforts by hardware and operating system manufacturers to make fundamental changes to network queues. There's also a proposal for a new back channel 40cp, the first such modification in many years, explicit congestion notification, or ECN. Fully extricating the internet from buffer bloat will draw on all of these changes and require the patience of many years. This is a long-term swamp, says Jetties. But there's a lot to look forward to about a post-buffer bloat future. With their inherent latency, buffers are bad for most interactive processes. When we speak via Skype, for example, we generally prefer an occasionally staticky signal now to a clear recording of what our caller said 3 seconds ago. For gamers, even a 50 millisecond lag could be the difference between fragging and being fragged. In fact, gaming is so sensitive to latency that all important gaming honors are still contested in person, with players boarding airplanes to gather and compete over a network serving just a single room. And much the same is true for anything else where being in sync matters. If you want to play music with your friends, even in your metropolitan area, you care about tens of milliseconds. Jetties notes, imagining a whole host of new applications and businesses that might spring forth to take advantage of the interactive potential of low latencies. A generalization I take away from this whole experience is that engineers should think about time as a first-class citizen. Apple's Stuart Cheshire concurs that it's high time for latency to become a top priority for network engineers. He's appalled that companies who advertise fast internet connections refer only to high bandwidth, not a low delay. By analogy, he notes that a Boeing 737 and a Boeing 747 both fired about 500 miles per hour. The former can hold 120 passengers, while the latter carries 3 times as many. So would you say that a Boeing 747 is 3 times faster than a Boeing 737? Of course not, Cheshire explains. Capacity does matter sometimes. For transferring large files, bandwidth is key. If you've got a huge amount of cargo to move, a container ship may well trump thousands of trips by a 747. For interhuman applications, however, a quick turnaround time is often far more important, and what we really need are more concords. And indeed, bringing latencies down is one of the current frontiers of networking research, and it will be interesting to see what that brings. Meanwhile, there are other battles to be waged. Jetty snaps his attention away for a second, looking out of the frame. It's not working for you? I'm talking to someone at the moment, and I'll deal with it when I'm finished. We're wrapping up here No, the 5 GHz is working at the moment. The 2.4 GHz channel has hung. It's the infamous bug. I'll reboot the router. Which seems an opportune moment to say our goodbyes and release our bandwidths to the commons, to the myriad flows making their additive increase. If you enjoyed this video and want to hear it again, be sure to click the subscribe button and also click the notification bell to switch between getting all notifications, and like and share. Leave your comment and suggestions below. Thank you for watching.